Right. So, very good morning to you all. I welcome you all for today's EMF session. So, without wasting much time, I will start the class. So, till now, 59 students were joined so far. Mhm. Right. So, in my last class, I have discussed magnetic energy. Right. So, magnetic energy or energy stored in magnetic field. Right. So, flux linkage or total flux passing through a circuit which contains n number of turns is given by equation 1, and flux linkage is directly proportional to current, and lambda is equal to Li, where L is inductance. From equations 1 and 2, equating equations 1 and 2, we will get inductance. L is equal to n pi by I. For a single turn, L is equal to pi by I. Right. So, and we know that the energy stored in an inductor is given by Wm is equal to half Li square, and this is equation 1, and where L is given from equation 3. So substituting L from equation 3, and we'll get equation 5. So in equation 5 we have pi and I, right? So where pi can be written like this: pi is equal to surface integral B dot ds, and I from Ampere circuital law, I is equal to line integral H dot dr. And substituting these two in equation 5 and simplifying, we will get this one: Wm is equal to half volume integral mu naught H square dV joules, or in other words, half mu naught H square is joules per meter cube. So this is the energy density, right? And before this, we have discussed the force between two parallel straight wires, and the force between two current elements also we have discussed, right? So these are the topics which I have discussed in my last class, right? And one more topic might be the last topic in this chapter is inductance, right? So as we have discussed capacitance in previous chapter in electrostatics, and here we will discuss inductance, right? So inductance under this topic I am going to discuss number 1, inductance of a coaxial cable. Inductance between two parallel wires. Third one, inductance of a solenoid, and inductance of a toroid, right? So these are 4 subtopics which I am going to discuss under inductance, right? So first one, inductance of a coaxial cable. Inductance of a coaxial cable. Do remember that the procedure is same for all 4, right? For all 4, the procedure is same. right? So same steps we will follow. So inductance and coaxial cables. What is meant by coaxial cable? Let me draw the figures first. So coaxial cable in the sense one inner conductor, one inner conductor. This is one inner conductor, and one outer conductor. One outer conductor. Right? So this is coaxial cable, and let us say that the radius of the inner conductor is A. This is the center. The radius of the inner conductor is A, and the radius of the outer conductor is B. Right? So therefore, to determine inductance, um, um, we will use ampere circuit law, right? So earlier for capacitance, we used Gauss law, and whereas here we use ampere circuit law, and we will determine inductance, right? And we know that we know that we know that energy stored in an inductor of Li square, right? Of Li square. Let us say this is equation 1, and energy stored in a magnetic field of volume integral mu naught h square dV, and let us say this is equation 2, right? So energy stored in an inductor, equation 1, and energy stored in a magnetic field is equation 2, right? So therefore both are energy, right? So therefore equation 1 and equation 2 can be equated. Therefore from equations 1 and 2, from equations 1 and 2 we can write half Li square is equal to half volume integral mu naught h square dV, right? And what we require? We require inductance. We are calculating inductance, right? So therefore L is equal to um, mu naught by I square volume integral h square dV. Let us say this is equation 3, right? Mu naught constant that can be taken outside the integration, and we have mu naught by I square volume integral h square dV, right? So therefore we need to determine magnetic field, and then substitute magnetic field in equation 3, integrate, you will get the answer, right? So magnetic field. So how to determine magnetic field? So here if you consider a coaxial cable, right? So in fact the magnetic field exists inside, right? Magnetic field exists inside. That means when A is less than rho is less than B, right? Magnetic field exists inside. That means in between A and B, and where rho is the radius. So therefore magnetic field exists in between the inner conductor and outer conductor, not outside. Outside the outer conductor or inside the inner conductor, magnetic field does not exist. Right? So therefore if rho tends to 0, right? If rho tends to 0, that will become a line. If rho tends to 0, that will become a line, right? So therefore, magnetic field due to a long wire, that we know, right? Magnetic field due to a long wire is equal to I by 2 pi rho, right? I by 2 pi rho, and where rho is the radius, right? So therefore, we can write H is equal to I by 2 pi rho, magnitude, right? I'm writing magnitude of magnetic field, right? So therefore, magnetic field due to a long straight wire is given by H is equal to I by 2 pi rho, right? I by 2 pi rho. Magnitude, I'm not indicating the direction. Magnitude, right? And let us say this is equation 4, and substituting equation 4 in equation 3, we get L is equal to mu naught by I square volume integral. Volume integral in the sense triple integral, right? Triple integral. H square is I square by 4 pi square rho square, and dV. What is dV? dV is volume in cylindrical coordinates, and which is given by rho d rho d pi dz, right? So that is the volume. So therefore, rho d rho d pi dz is the volume, right? And rho is the radius. Radius varies between A and B, right? Radius varies between A and B, and pi varies between 0 to 2 pi, and z is the length of the cable. Therefore, 0 to L, let us say the length of the coaxial cable is L, right? So therefore, rho, pi, and z limits are these. So rho is the radius which varies from A to B, and pi in between 0 and 2 pi, and z is the length of the coaxial cable, or the coaxial inductor, and is 0 to L, right? So therefore, simplifying this, so this is equal to mu naught by 4 pi square. I square and I square will get cancelled, and 0 to L, 0 to 2 pi, and A to B, rho and rho will get cancelled out, and we will be having rho 1 by rho d rho d pi dz, right? So integration of 1 by rho d rho, right? Integration of 1 by rho d rho is a log rho, right? Is log rho, and substitute the limits, will get log b minus log a. Therefore, log b by a, right? Log b by a you will get, and integration with respect to pi is pi. And substitute the limits, you will get 2 pi, and integrate with respect to z is z, and substitute the limits, you will get L, right? So substituting all those values, and finally you will get L, right? L, I will give you mu naught L by 2 pi ln b by this you will get. Then so this is the final expression, right? So L is equal to mu naught L by 2 pi log b by a. So this is the final expression for inductance of a coaxial cable, right? So very simple. So these equations we know, equation 1 and equation 2 are the energy stored in inductor and magnetic field respectively. Those equations we know, and equating those two, simplify, you will get equation 3, and equation 4 already we know, right? So equation 4 is nothing but a magnetic field due to a long wire, a long straight wire that we have taken directly, right? Because coaxial cable is nothing but a long wire. So therefore, magnetic field due to a long wire, directly that expression we have taken, and that is substituted in equation 3 and integrated accordingly. You will get the answer. Very simple, right? And second one, inductance between two parallel wires. Inductance between two parallel wires. Second one, inductance between two parallel wires, right? So let us consider two parallel wires. So two parallel wires, same wire, same type of wires. So let us say this is one parallel wire, and another parallel wire, and assume that these two are separated by a distance t, right? These two are separated by a distance d, and the radius, so this is the center, right? Center, and the radius is a, right? So this is, let us, so this is the center axis, so this is the center axis, right? And the radius, right? The radius means from here to here. So this is from center to edge, right? From center to edge is a, right? From center to edge is a, right? So a is the radius. Then similarly, this edge is this one, right? So a radius is a for both, radius is a, right? So we are considering same type of conducting wires, and they are separated, right? They are separated by distance d, right? So therefore the distance d in the sense from here to here, from this edge, right? From this edge to this edge is d, right? So therefore from here to here, right? From here to here, from the center of this one, from center of this one to here to the edge of the other one is d minus a, right? Is it clear? Right? D minus a. right? So radius of each conductor, explaining once again, radius of each conductor is a, and two long conducting wires are separated by a distance d, and the distance from the center of one conductor to the edge of the other conductor is d minus a, right? So therefore the inductance, right, inductance, again the same procedure. So Wm is equal to half Li square, and this is equation 1, and Wm is equal to half volume integral mu h square dv, and this is equation 2, right? So here it is mu, right? So make a note here, here it is mu, it is not mu naught, right? So you can remove mu naught. Why? Because they are separated by dielectric material. Inner conductor and outer conductor are separated by a dielectric material, right? So therefore it is an inductor, sorry, it is a dielectric media. If the medium is air, then it is mu naught, right? If medium is air, then it is mu naught, right? So now equating equations 1 and 2, as we have done above, same steps, right? So here equation 1 is same, equation 2 is same, and equation 3 is also same. So therefore I will take equation 3 directly, right? So L, from equations 1 and 2 you can find out L is equal to mu by I square volume integral h square dv, right? So this is equation 3, right? This is equation 3. And magnetic field. So what is magnetic field? So here magnetic field H is equal to I by 2 pi d. Again same, H is equal to I by 2 pi d, because it is a long straight wire, right? It is a long straight wire. So coaxial cable is also a long straight wire. It comes under that category, right? Two conducting wires, and here also two conducting wires. Therefore whenever um, it contains long wire, then magnetic field is I by 2 pi, right? So d is the distance between those two conductors. I by 2 pi d is the magnetic field, right? So therefore L is equal to mu by I square h square is I square by 4 pi square d square rho d rho d pi dz. Now what are the limits? What are the limits? So limits are different here. Then so here the limits are a to d minus a. That is only the difference between the previous one and this one. Pi 0 to 2 pi, and z 0 to L, right? Length of the conductor is L here. So length of the conductor is L. L is the length of the conductor, right? So these are the limits, right? So I hope you find the difference between this the above, this one and this one. Here the limits, right? So limits here a to b, row limits are a to b, right? A to b. But whereas here limits are a to d minus a, right? Limits are a to d minus a. That is only the difference between this one and the above topic, right? So therefore, integrating and simplifying, right? Integrating and simplifying, we will get mm, we will get mu L divided by 2 pi L d minus A by A, right? D minus A by A, right? So this is the inductance due to one wire, right? Due to one wire. So here this is the magnetic field due to one long wire, right? One long wire. And as we are considering two such long wires, right? So since the two wires are symmetrical, since the two wires are symmetrical, then we can write L is equal to 2 times 2 times of mu L by 2 pi ln d minus A by A, right? So therefore L is equal to mu L by pi log d minus A by A, right? So this is the expression for inductance, right? Inductance between two parallel conducting long wires, right? Two parallel conducting long wires. So this is how we can determine inductance, right? So very easy, right? So same procedure we have followed, right? And next one, third one, inductance of a solenoid, right? Inductance of a solenoid, right? So solenoid. So what is solenoid? So solenoid is so this is a magnetic material, right? So this is a magnetic material, magnetic material, right? So this is a magnetic material wounded by, surrounded by, or wounded by conducting coil, right? Wounded by conducting coil, right? Wounded by a conducting coil with a number of turns, right? Is called as a solenoid, right? So this is a solenoid, right? So magnetic material wounded by a conducting coil, and the length of the magnetic material is L, right? Length of the magnetic material is L, right? So this is a solenoid, right? Um, a magnetic material of length L wounded by a conducting coil of n turns as shown is called a solenoid, right? It's called a solenoid, right? And to determine inductance of a solenoid, so again same procedure of Li square, and this is equation 1, and Wm is equal to half volume integral mu h square dV, or this can be written like this: half mu h square V, right? So where V is volume, right? Where V is volume, right? So V is nothing but volume integral dV, that is volume, right? Volume integral dV. So this is volume, right? So because we are assuming that the field is uniform, right? So when field is uniform, which can be taken outside the integral, and we can write this one, right? So this is only the small difference between previous one and this one, right? So from equations 1 and 2, we have half Li square is equal to half mu h square B, right? And therefore L is equal to mu h square B by I square. Let us say this is equation 3, right? So this is inductance, and now and determine H, right? Determine H, right? So magnetic field of a solenoid can be determined from Ampere's circuit law, right? Ampere circuit. So what is Ampere circuit law? Closed integral h dot dl is equal to I, right? So this is Ampere circuit law, and it contains n number of turns, right? Solenoid, it contains n number of turns, so therefore multiplied with n number of turns, and we are assuming that the field is uniform, so therefore h can be taken outside. L dl is equal to in, right? And h is equal to in by line integral dl. So what is line integral dl? Line integral dl is length, right? So length L is equal to line integral dl, right? Volume integral dl is volume, right? So this is volume, right? So this is volume, and line integral dl is length. Surface integral ds is surface area, right? So therefore, what is the length of the solenoid we have considered? The length of the solenoid we have considered is L, right? Here in the figure you can see the length of the solenoid is L, right? So therefore L. So therefore H is equal to In by L. Let us say this is equation 4. Therefore, substituting equation 4 in equation 3, right? Substituting equation 4 in equation 3, we will get L is equal to mu V by I square H square, I square N square by L square, right? And this is equal to mu N square V by L square. This is inductance, right? Or L is equal to mu N square S by L, right? Mu N square S by L, right? Because volume. So what is volume? Area into length, right? Area. S is area and L is length and V is volume, right? So therefore volume is equal to area into length, that we know, right? So therefore V is equal to SL, and L and one L will get cancelled and we will get this one, right? So L is equal to mu N square S by L is the expression for inductance of a solenoid, right? So this is how we can and next fourth one, right? So fourth one, inductance of a toroid, inductance of a toroid, right? So what is a toroid? So toroid, so this is a magnetic material, right? So this is all a magnetic material, right? So this is a magnetic material, right? And wounded by a coil, right? Wounded by a coil like this, right? Like this, right? So winded by a coil like this as shown, and it is called a toroid, right? It is called a toroid, right? And let us say the radius, this is the radius R, right? Radius R, right? And inductance due to a toroid, say I'm taking the same equation here, L is equal to equation 3, right? Equation 3, I'm taking equation 3 as it is. L is equal to mu H square V by I square, right? L is equal to mu H square V by I square. Let us say this is equation 1, right? And where V is volume, right? V is volume, that we know. H is magnetic field, and now we need to determine magnetic field, right? So magnetic field due to a toroid, magnetic field due to a toroid, again can be determined from Ampere's circuit law. H dot dl is equal to I, right? And Again, it contains n number of turns, right? So H is equal to IN by DL, right? Line integral DL. And this is equal to IN by line integral DL. So what is line integral DL? What is the length of the toroid? So length of the toroid is nothing but here it is circumference, right? Circumference of a toroid, right? So it is like a circle like structure, right? And whose radius is r. Then what is circumference? So circumference is 2 pi r, right? Circumference is 2 pi r. So therefore H is equal to IN by 2 pi r. Let us say this is equation 2, right? So therefore substituting equation 2 in equation 1, we will get L is equal to mu V H square, right? Mu V by I square H square. H square is I square N square by 4, let us say 2 pi r whole square, right? So simplifying this, so this is equal to mu n square V by 2 pi r whole square, right? So this is the inductance of a solenoid. Further, volume. So what is volume? Volume is area into length, right? Volume is area into length. What is length of a toroid? Just now we have discussed. Length of a toroid is circumference, right? Here it is circumference. Therefore, volume, right? Volume V is equal to S into 2 pi r, right? So if you substitute this, what you'll get? L is equal to mu n square S by 2 pi r, right? So this is the final expression for inductance, right? Inductance of a toroid, right? So this is how we can determine inductance, right? So in this class, I have discussed inductance. Under this 4 subtopics we have discussed: inductance of a coaxial cable, inductance between 2 parallel wires, inductance of a solenoid, and inductance of a toroid. And the procedure which we have followed is same to all the 4, right? Is same to all the 4. Therefore, inductance of a coaxial cable is this one, right? And inductance of a 2 parallel wires is this one. Inductance of a solenoid, right, is this one. And inductance of a toroid is this one. So this is how we can derive or find out the inductance of different types of inductors, right? So let me wind up this class as the time is already 10, right? So just a minute.